We'll wait for 5 minutes so that people can join, and we'll just wait for more people to join. We'll wait for 2 more minutes because I only see 5 people here. So let's just see if any more people are joining. In the meantime, if anyone has any doubts, we can discuss. So any doubts or clarifications, if you have, please put it in the chat or unmute.
Good evening, ma'am. Hello.
Yes, go ahead.
Ma'am, I'm Godhuli. I had a question that uh, about the final examination, about if it will be in MSQ or MCQ type. You said to ask it in the question forum. So I asked that, but they didn't give any answer. So can you help to know about that?
Okay, I also don't know about it. Maybe I can mail the respected. You tried mailing the professor and or the NPTEL people? You can try mailing them. I will also try to drop a mail about it, and I'll let you know by Monday's class if they reply. I don't know if they will reply. Whenever they reply, I can post it in the next class.
Okay, ma'am. Thank you.
Okay, sure. So, what is your exam date for
Ma'am,
this
it's 24th March.
24th March? Okay, okay. Yeah, I'll mail them today. They usually don't reply on weekends. So Monday probably I'll come to know. Anyway, Monday we have a class, in which case I can tell you then. Otherwise, I'll tell them to inform you or something. Let's see.
Okay, ma'am.
I'm muted. Okay. I hope you can hear me. Yeah, I was saying that we can start the class and people can keep joining. So I'll just share my screen. Okay. Uh, Hello everyone. So again, welcome back to another one of these problem solving sessions. By now we are well into the course and we are almost at the end of the course actually. So you are familiar with what this sort of session is. My name is Zenia. I am a PhD student at ISC and I have been conducting these sessions so that you can, have a quick revision of the concepts and also kind of, quick revision of the concepts, and also it will help you to solve your assignments, which will ultimately help you in your final exam also. Okay, so I'm sorry about again having to keep a session in the weekend. I was at a conference this past Monday and I could not avoid it. And somehow I did not get a slot in the weekdays. So that's why it's on a weekend. So, yeah, thank you all for making time on your Saturday to join the class. And as always, if any of your friends are unable to join because of the changed time schedule, I am always recording these sessions and putting them on YouTube, and also the slides of the sessions have been available. So I hope that's all being useful to you, and all the links are maintained on my page so that you can have easy access to it as well. So, right. So so now we can go on to the class. So in the previous class, we talked at some length about, first of all, hydrogen burning. And just to remind you, burning, when we say burning as a nuclear physicist, we mean basically fusion reactions. And last week we saw that, or, whatever the last class was, we saw that hydrogen fusion can happen, is the first step that happens in all main sequence stars, first of all. We know that we need some sort of nuclear fusion to balance the inward push of gravity, and that is hydrostatic equilibrium, and that we have discussed at length in the first class. So we see that the very first stage of hydrostatic equilibrium, the energy is provided by the energy released during hydrogen burning or hydrogen fusion, where four hydrogens or four proton merge to form one helium atom, and this releases around 26 mega electron volts, and that energy is used to stabilize the star. Now, as we also saw in one of the previous lectures, you saw that stars have a life cycle, and once the main sequence burning, I mean, once the hydrogen fusion has reached its limit, once the hydrogen of the star is used up, the star does not immediately collapse into a black hole or some other configuration, right? Because there can be, depending on the mass of the star, there can be further stages of burning, and this is something we looked at in great detail. So if any of you I would say that during this lecture, we are going to encounter a lot of things we saw in the early lectures. And I would say that you can kind of look at lecture 2 particularly, because that can kind of give you the context. So that time we were just talking about burning, but now we are actually looking at what are the mechanisms behind that nuclear burning itself. So, yeah, so basically we have this, once hydrogen runs out, the star contracts because gravity and pressure are not balanced anymore. And if the star is massive enough, which it can go to further stages of burning. So you saw that there is some sort of threshold for every process to happen. So even for hydrogen burning, there were kind of two reactions that we saw. One was this PP chain and the other was the CNO cycle, right? And we saw that there is a threshold beyond which the CNO becomes more efficient than PP. And because based on that, we were saying that, okay, massive stars can undergo CNO, whereas stars like our sun undergo PP. So similarly, there are thresholds for every burning to take place. So for helium to fuse to carbon, there is a threshold. Carbon to fuse to oxygen, there's a threshold. And as we saw last time, the threshold temperature can be related to mass. So that's why only very massive stars can fuse elements all the way up to iron. And why is iron the limit? I think we have already discussed in the class. So anyone wants to say that why iron is the limit of why of that stars can synthesize elements in their pores, and the sequence goes: hydrogen fuses to helium, helium goes to carbon, carbon goes to oxygen, etc., up to iron. So beyond iron there is no fusion taking place. So anyone wants to say why that is, can put your answers in the chat. I will just join from my phone also so I can monitor the chat. Join, add this to this. I think you should know this, and this would have been covered in your lectures already. So why? So up to, okay, I hope you understood the question, right? So in a any main sequence star, we can, depending on its mass, we can fuse elements, and you can fuse higher and higher elements. But no matter how massive the star is, the fusion only takes place till ion. Beyond ion, we don't see any elements fusing within the star itself. So why it's ion the limit, or why ion fusion is the limit? Can anyone put it in the chat, or you can unmute and say? Does nobody know the answer? That is very surprising. I think you know the answer. Maybe you guys are, you know the answer. We have discussed this already. After ion fusion becomes endothermic. Yes, that is the answer. Correct. So again, what we need is, so as Vivek says, what we need when we look for a fusion reaction here is that we need a release of energy, which is what is called an exothermic reaction. And because we need something to push outwards against the inward push of gravity, right? So for ion, it does not release energy, rather it takes up energy to fuse ion, right? Another way of understanding this is the binding energy curve. So I don't have a picture right now, but maybe in some of the, I think in one of the later slides or videos I have it. But this is also there in your 12th standard. Basically, if you draw the binding energy per nucleon with the atomic number, then you will see a graph which is peaked at ion. And ion has the most binding energy per nucleon. But what does that mean? That means that ion is really stable, right? So what does, whenever a nucleon undergoes fusion, like when hydrogen fuses to helium, it releases energy because helium is a more stable, or it's a lower energy state when compared to the four individual hydrogen atoms, right? Whereas for ion is the peak. There is nothing that is more stable than ion, and that is why it does not go and undergo fusion or fission easily. Okay, so the rule of thumb is that everything in the universe wants to kind of, get to the lowest energy state, or the most stable state, I would say. So ion having a very high energy and binding energy, I think in one of the earlier lectures we have already discussed. Binding energy is basically the energy you have to supply to break apart something. So when ion has a very high binding energy, that means that I need to do a lot of work to break it apart. So it is very stable. So that is the kind of idea that you need to have. So we look at in this lecture this kinds of processes that lead up to the fusion reactions up to iron. So we have already looked at hydrogen to helium in some detail, and as I said, this is the longest phase of a star's life. So there are, a lot of things that we have to consider, but also the other reactions are also interesting, and we can look at them. And we'll also look at S and R on those other processes. I think you have already looked at it in your lecture, and also the higher order nucleosynthesis reactions. So essentially, we have now reached the realm of looking at, if you remember, I had shown you a periodic table a long time ago, and I think now we are in a position to understand how each elements of the periodic table comes astrophysically, right? Or what is the origin. So yeah, this is the kind of context that we should have when we are looking at these things. So again, we are now very much in the nuclear physics part of things, but I just wanted to remind you that everything has a linkage back to astrophysics and whatever we had been discussing in the early lectures as well. So this is kind of like, this is basically, again, we are doing the stellar evolution, but from the point of view of nuclear fusion reaction. What are the actual reactions which are taking place? Okay, so another important thing we saw last time, and I wanted to emphasize it again because it's quite important, is the two kinds of ways in which we can describe nuclei itself. So this is the liquid drop model, and we actually last time, again, if any of you were not there last time, you can go and see the video. But we have discussed in detail how each of these terms come, and particularly how their dependence on the atomic number, sorry, not atomic number, the atomic mass number comes about. And you know that atomic mass number is directly related to the radius through a scaling. So we were able to see that this liquid drop model explains the energy, and it helps us to intuitively understand fusion, etc., fusion and fission. But it did not help to understand this magic numbers and all those spin parity, all those things that are associated with nuclei that we see experimentally. And for that, we had to go to the shell model. And you know that for the shell model, the most underlying assumption was this statement, which is that each nucleon, so we consider, as I said last time, in an atom, it becomes easy to model the motion of electrons because they are governed by a central body, right, which is kind of controlling them. Whereas in a nucleus, there is no such central body, there is no nucleus inside a nucleus, right? So there is, all the nucleons are moving. But what we can do is we can just look at one of the nucleons at a time and consider it to be moving in a field produced by all the other nucleons. Again, we discussed this in a lot of detail last time. I would encourage you to go and watch the video, but because there's been a little bit of a gap, I thought we can talk about it again, because this is very important, and this is a very essential, this is the most basic part of what you have studied, right? The nuclear physics part. So we saw how to model it, and we found that, because there are these, because now we can consider quantum states, and because crucially all nucleons, whether they be neutrons or protons or fermions, there are only a fixed number of nucleons that can fill every state. And the reason for that was the Pauli exclusion principle. So again, you can see how all the lectures are connected, because Pauli exclusion principle we spoke about, I think, when I briefly introduced Pauli exclusion principle when I was motivating compact objects to you, but I also discussed it in the context of Maxwell-Boltzmann distribution. So someone had asked about Maxwell-Boltzmann distribution and such. So again, I think lecture number 3 or 4 is a complete introduction to Maxwell-Boltzmann and also talks about this. So everything is interconnected. So I think it's good that it's interconnected in the sense that we all can give context to each of the lectures we're studying. They are not all in vacuum. So anyway, so this is the liquid drop we saw. This is the shell model. And when the shells are fully filled, we get magic numbers, which are extra stable, which means they have higher binding energy per nucleon, as we discussed for the ion case. So, and then Of course, you saw how to calculate the properties of nuclei using the shell model. You saw it is the unpaired nuclei which matter. And from that, we were able to find the spin parity. And this is the energy level diagram. And based on the multiplicity, etc., we learned how to fill the states. So again, I don't have any quick way for you to memorize this sequence. All I can say is that you should memorize at least up to 50. That might be useful for you. And the higher order spins always have a lower energy when compared to the higher things. So you should just remember, try to remember and recall this. If you find some trick, please share it in the chat so that me and your friends can also benefit. So once again, I'm saying that all these concepts are, kind of involved in the sense that they involve, they are, a little higher order, and also they involve fair bit of quantum mechanics. So if you find it difficult to follow the basics, or if you want to get some more clarity, I would suggest that you can look at, first of all, there is a very nice nuclear physics textbook by Kenneth Crane, which I would recommend and that I used for my MSc. But apart from that, I would say that if you want to get your quantum mechanics stable, like for example, even apart from the nuclear shell model, we had discussion about quantum tunneling and square well potential and so on. So if you want to understand those topics, I would say that you can look at Griffiths as a quantum mechanics textbook, which is a very nice book for concepts. And Zetley also has concepts, but it also has a lot of solved problems which can help you. So I don't know if this is directly applicable to your exam or not. From that point of view, I don't know if these textbooks are strictly required. But I will definitely say that if you have an interest in the field and if you have an interest in physics in general, quantum mechanics is the cornerstone of much of modern physics, and it is good to understand. And I think these two books really sum it up really well. So a few people had written to me about square well and finite well and tunneling. So unfortunately, I don't know if I can accommodate those things. We'll see. I'll try to see if I can take a little bit of it. But again, that those are things where intuition itself doesn't work, because quantum mechanics, first of all, is not intuitive. That's one of the things. And the other thing is, those are things where it is required that you sit down and solve it with a piece of pen and paper. So like the finite well, for example, you can find out what is the transmission probability, the refraction probability, and so on, by matching the wave functions and putting boundary conditions. And it sounds complicated, but it boils down to solving a set of linear equations at the end. So I would say that you should try to pick up one of these books or any other quantum mechanics book. This will be present everywhere. There are good lectures also online, and I would say that you can just try doing those problems for once, right? Because there is because visualization does not get you very far in quantum mechanics, because by its nature, quantum mechanics is the science of those things which we do not see and which we do not interact with in our daily life. So in that sense, we do need to at some point get into the mathematics. Okay, so I think we have got some intuition for things from the small small things which I've told you, but doing the maths is always better as well. So okay. So yeah, so that is about what all you have seen so far, and just some things, because I got like a few mails about this quantum mechanics and square well particularly. So I just wanted to make that clear. Let's see about whether we can have a session on quantum mechanics, but I think that will kind of deviate from the course. So it will be better if you can pick up these, and if you want more resources, you can mail me and I can always help you out. Okay. There's also a book called Quantum Mechanics in a Nutshell or something like that. I forgot. Yeah, that's by Suskind, but that's a little bit higher than you require. So I think you don't have to go it. I think starting with Griffiths is a good idea, and Zetley is also very well written. So you can try those two. Okay, so yeah, so with that long introduction, I think we can go to the topic of um, today's problem solving session, which is about higher order nucleosynthesis. And by higher order nucleosynthesis, I mean fusing elements other than hydrogen, right? So we already saw PP and CNO cycle, which are both ways of fusing hydrogen to form helium. So the next stage of a star's evolution would involve the fusion of helium. So how does helium fusion take place? So helium fusion takes place through something called the triple alpha process. And here you can see why it's called that. So alpha particles are basically helium nuclei. They are another name for helium nuclei, and you should be familiar with this from even school when we learned about this Rutherford's alpha scattering experiment. He sent positively charged alpha particles, and they are positively charged because they are basically helium nuclei, right? So what happens is helium fuses or two helium particles interact, and you can see that there is a release of energy and they form beryllium. And during this beryllium interacts further with another helium to give carbon 12 with release of energy. So there are basically three helium nuclei involved, and that is why this is called the triple alpha process, because there are three alpha particles which are eventually giving one carbon atom. And carbon is a very important element, right? We say, the whole science of organic chemistry is based on carbon, and that's because most of the or all the life forms that we see on earth are carbon based. So in that sense, from the point of view of understanding of life and those kinds of arguments, carbon becomes a very important element. So the formation of carbon in stars is also very interesting, because as finally whatever is formed in the universe has only come to us and formed us, right? So there's a famous quote of "we are made of star stuff." So essentially it is this process which has led to the formation of the carbon, which has eventually formed all the carbon based life forms, basically all life on earth that we see around us. So understanding this process was a very key discovery of the early whatever the years of stellar nucleosynthesis. And I think this was discussed in the class as well. There was one of the very pioneering people in this field was Fred Hoyle, and the way that he was able to kind of resolve a mystery about the triple alpha process, very interesting. So right. So this is basically a diagram that I think I showed something like that like this last time. This is energy release as a function of temperature. So here again, you can see how the temperature and the reactions are related. You can see that for the sun, for example, the output from the PP chain is much more than the output from the CNO. And that's why PP dominates in our sun. But if you go to higher temperatures and more massive stars, you can see that at some point the CNO cycle dominates, and that's why in massive stars we see that. And of course, for the fusion of helium we require more temperature, because these are more massive particles, and we need more temperature for their fusion. Because if you remember from your basic calculation, you know that there is a essentially a Coulomb barrier that we have to overcome, right? And if we have more atomic number, that means more the Coulomb barrier is higher, and also it becomes more things. So after hydrogen fusion, you know that we need higher temperatures to start off triple alpha, and that is what is kind of shown here. So after hydrogen fusion and helium fusion takes place, and it takes place in that sequence because based on the temperature. So that is what is happening. Okay. So the point is that with the fusion of beryllium, as I said, it is fusion of helium is not very simple. Basically, the problem was that the beryllium lifetime is very short. And because of this, people were worried that beryllium might not fuse, for further or something like that. So it's not so simple, and one of the things that was proposed is that if unstable beryllium is struck by another helium nucleus, then it forms carbon 12 and releases energy in form of gamma ray. So the thing that was important here is that the lifetime of the beryllium was longer than the collision and scattering of helium nuclei at the temperature. So we need the lifetime to be longer, so beryllium exists for at least that long, that it undergoes the reaction, right? So that was a criterion here, that beryllium has to live long enough that it is able to interact with one more carbon and form a gamma ray. Sorry, not one more carbon, one more alpha particle. So as I said, carbon, is one of the most abundant elements in the universe, and it's also of central importance when we talk about life and all that. So people are not very comfortable where this sort of mechanism did not seem very, what can I say, it seemed like it was a little more unstable than they would have liked. So what happened was, there was this theorist, his name was Fred Hoyle. He was a theoretical astrophysicist, and he was the one who suggested that, you know, maybe there is a resonance state, or there is a carbon 12 state where its energy is very much near the beryllium and helium nucleus, such that it becomes a resonant reaction. And he proposed this and called it a Hoyle state. And his reasoning is very interesting, and we'll get to it in a second. But the point is that he said that based on the fact that I see carbon all around me, I know that there should be something more in the mechanism which is helping this reaction, or which is making this reaction a little more efficient than it seems from outside. And that's why he proposed this Hoyle state, and he actually predicted what should be its exact energy. So he said that, it might be that there's a carbon 12 nucleus which has energy exactly or very much near to the combined combination of beryllium and helium, such that when they fuse, there is a small possibility that they form this carbon 12 state, and then it finally decays to the ground state of carbon 12 that we see. So he was talking about this excited state of carbon 12, which is now called the Hoyle state. And this would be a resonant reaction, and that would enhance the possibility of this reaction happening. So, and the nice thing was that this resonant energy state was actually eventually found by experiments at Caltech. And this is kind of a remarkable thing if you think about it. And I have seen people call it the most outrageous prediction ever in a nuclear synthesis, because, there was no reason to believe. We did have a mechanism to form carbon 12. There was no reason to believe that, we had a resonance state. But Hoyle had the insight to say that, the fact that carbon is so abundant means that there must be something that is helping triple alpha beyond what we see. So he had that insight. And, this is why both theoretical formulation and experiments are important. And we often think that science follows in a way where, there is a experiment, and then some sort of discovery, and then we have to come up with a theory to explain that discovery. But this is a good example of when things happen in the other way as well. Sometimes theorists can predict things, and the experiments have not caught up to them yet, and then it can be that after a few years, when we are advanced enough, we can find out whether I was true or not. So a more extreme example of this would be Einstein's theory of general relativity. He proposed it all the way back in 1915, and at that time there was no stringent test of it, but it actually took 100 years for the first gravitational waves to be detected. So yeah, so sometimes theory can come before experiments, sometimes it's the other way around. So yeah, the point is that there is no upper standing for either. We need both of them to do good science and to do good astrophysics. So this is essentially a diagram of what happens. So you can see that beryllium, an alpha particle, might form a carbon. So this is the Hoyle state. And 99% of the time, the Hoyle state might decay back into the beryllium through alpha decay. But a small amount of the time, it relaxes back to the ground state of carbon 12, which is what we actually measure, right? So this 7.65 MeV state is the Hoyle state. It has a parity of 0 plus, and this is exactly the special state that he proposed. So instead of going from here to here, there's an intermediate step which we may not be able to see as the end result, but plays an important role. So this was Hoyle's insight. And Hoyle's uh, proposal is actually very interesting because it is based on something called the anthropic principle. So the anthropic principle is a very interesting mix of, I would say, science and philosophy. So essentially, the anthropic principle says that, sometimes things in physics look very fine-tuned, right? Like, for a simple example is that Earth exists at exactly the correct distance from sun that we should have liquid water. If Earth was in the position of Mars, or if it was in the position of Venus, we will not have liquid water on our surface, and we would not, and we know that water, as we understand it, is one of the key ingredients of life. So people say that why should it have been that Earth is exactly at the place where liquid water happens? So the argument that anthropic principle makes is that if water did not exist on Earth's surface, then none of us would have existed to observe it in the first place. So there are probably many hundreds of other systems where there are Earth-like planets which are in different parts around the sun, and the point is that there only in the very special systems where we actually see um, capacity for life to come can we then uh, observe it. So so it is not like a special thing that the Earth is at the third position such that it has liquid water. Only if it was like that, then only we can interpret the world, right? So that is kind of an idea of the anthropic principle. Again, this is more of a philosophy than a physics, but it is a good way to think about the science of, when we think about the universe at large or something, people kind of invoke this principle. So what Hoyle said was, Hoyle said, and Hoyle was a very strange man in the later parts of his life. He was one of the people who was actually against the Big Bang theory, and he had also made some wrong statements. But what he said about this particular his discovery, which is again very important and very gave us a really good insight into the formation of carbon 12. He said that a common sense interpretation of the fact suggests that some super intellect has monkeyed with physics, chemistry, and biology, and that there are no blind forces speaking about in nature. So it's kind of the way that he kind of applied a version of the anthropic principle, in the sense that he said that since there is so much carbon 12 around, since I am alive and I am a carbon based being, carbon 12 formation should be taking place in this special way, and it should be taking place in a more rigorous way than we have been thinking about. So I have also attached some articles which kind of explain how important the Hoyle state is and give some of his insights other than this as well. So I think it's an interesting thing to think about if you are interested in science. And one thing that's always interesting, and that we should learn as scientists and as people who are interested in science, is the history of science. So we only learn about a few great people and we think that they discovered their things, like Newton had an apple fall on him and he immediately discovered gravity, but that's not the case. There is always a lot of people. Almost all science is collaborative and almost all science involves a lot of struggle. So I think when we go back and we try to read about those stories, especially the stories which don't come out in the mainstream, right? The stories which are not had the chance to come and become so much known, like Newton's apple tree story. When we have the opportunity to look for stories, it helps us also. We think that, okay, this great person was also stuck on a problem once upon a time. It's not just me, it's about physics, right? So yeah, so that was a deviation, but the point is that this is based on something called the anthropic principle. In simple words, it says that the conditions, when we observe something, the conditions should be such that that observation can take place in the first place. Basically, whenever I observe something in the universe, that ensures that the universe has been constructed in such a way that I can exist in the first place. Otherwise, who will be making the observation? So there are, this is not like a fully accepted way of thinking about the world. People say different things about different have different viewpoints on this, but I thought that this is a nice way to introduce this kind of thinking into the course as well. Again, maybe not relevant from the point of view of an exam or anything, but still interesting nonetheless. So as we were discussing, the threshold for triple alpha is little higher. The temperature for the triple alpha process to start is kind of higher when we compare with the temperature of the hydrogen process. That makes sense, right? We first fuse hydrogen and then we keep on fusing it, and once enough helium has built up in the core and the core is hot enough, then only can we start the next phase of nuclear burning. So it happens in kind of stages. So as you can see, the triple alpha process occurs in red giant stars. So again, if you remember, like they have left their main sequence already, they have consumed their core hydrogen and have core temperature of 10 power 8 Kelvin and higher. So red giant is the phase where, you know, hydrogen burning has exhausted in the star, so the main sequence is over. So because of the lack of pressure balance, the star actually collapses, and this collapse can cause the temperature to increase and the outer layers to expand. So again, we had discussed red giant and other supergiant phases in detail in the stellar evolution class, which if I remember correctly, it is the second class that second of the TA session. I would encourage you to go watch it. I also showed you a video of what will happen to the sun when it's hydrogen fuel, when it comes out of the main sequence, and that is exactly what will happen. It will become a red giant, and it will eventually end up as a white dwarf. So yeah, please go and refresh your mind about that. So point is that we need 10 power 8 Kelvin and higher to fuse helium. And that will of course form carbon 12. Once carbon 12 is formed, then if we go to even higher temperatures of 10 power 8 Kelvin or so, we can now form then two carbon can fuse to form oxygen, neon, and then, you know, again, after carbon forms oxygen, then oxygen can fuse to form silicon, phosphorus, and sulfur isotopes. So the point is that we always, you know, as I said, it happens in kind of stages, right? The next nucleus always needs a higher temperature to fuse. And once it forms, then we have to then, you know, once a certain element has been depleted through fusion, then we have to contract the core. And, you know, all these processes keep happening in the star. The core contracts because the pressure balance is disrupted, and that drives up the temperature, and that can ensure that the next stage happens. Sometimes the next stage may not happen also. As we discussed in detail in our stellar evolution class, it depends on how massive the star is. And we saw that there are actually two branches of how a star can evolve based on its mass, whether it ends up as a white dwarf, which could end up as a type 1 supernova, or it goes through a type 2 supernova phase because it has fused elements all the way up to ion, and core collapses to a type 2 supernova, and eventually it forms either a neutron star or a black hole. So yeah, so these are all about this nucleosynthesis that is happening inside a star itself. So yeah, so this you can see exactly what I was talking about. This is your carbon burning. So you can see that, one second. Right. So you can see that the reactions happen in shells inside stars, right? So it's like the core hydrogen gets depleted, but there might be hydrogen burning still happening in the layers. Like that, the core of the star is now helium when it first crosses from the main sequence. Then we have triple alpha happening and forming carbon in the core. So again, the core becomes more and more carbon dominated. Then there is helium burning happening in the outer layers of the core, like in a helium burning shell. And then once the carbon is, you know, depleted, it becomes oxygen neon, and here we have actually got a inert oxygen neon magnesium core, and that means that this it will eventually end up as an oxygen neon white dwarf. The reason is that this star may not have been massive enough that it can contract enough to initiate oxygen to burn to sulfur and those other stages. So here you can see exactly how carbon burning can lead to neon, sodium, and magnesium. And you can see that it starts from around 610 power 8 or 510 power 8 Kelvin. And these are the higher order burning that you can see. You can see that neon burns and gives oxygen. This is basically alpha decay, because again, you should be familiar with these kinds of reactions now. You can see that there is a release of you can see that alpha particle is given out. Here alpha is captured, and, you know, some magnesium is formed. Here you can see neutron is captured to form neon, but a higher isotope, and so on. And that isotope can eventually lead to even higher isotope of neon, higher mass isotope of neon. Apart from that, we also have possibility of oxygen. So you can see that oxygen can give different kinds of elements like silicon, sulfur, and phosphorus. So you can see that this takes around 1 billion Kelvin, and you can see that at about 2 billion Kelvin, oxygen core can transform into silicon, phosphorus, and sulfur core. So in the previous slide, it's possible that this was a low mass star and it never really reached 2 billion Kelvin through its mass contraction, and that's why we have this oxygen neon magnesium core. So again, this is kind of what we exactly the thing that we discussed last time when we talked about this what is it called, the stellar evolution, and the sort of two branches of stellar evolution that a element that a star can take. So if a low mass star, the fusion happens up to a certain point, maybe up to oxygen or up to carbon, and beyond that the star is unable to fuse because of its mass. Whereas in high mass stars, the reactions happen all the way up to ion, and once ion forms and it starts to collapse, then we get an extreme violent discharge of energy, and that is what's called a supernova. So as I said, like there is a very complicated reactions that happen in supernova. I mean, the formation of supernova, I have linked to a video later, and we can watch it also to understand. So basically, beyond the formation of carbon, it's also sometimes called an alpha ladder, because you can see that alpha particle capture leads to higher and higher elements. And through this process, even though ion and ion can fuse, but ion may capture an alpha particle to give nickel. So you can see how, this is of course all the reactions that we have seen so far. This is your proton-proton chain, which is of course your PP chain. This is your CNO cycle. Both of these give us around happen around 10 power 7 or so Kelvin, and you can see that they give us helium. And then if we reach to an order of magnitude higher, about 10 power 8 Kelvin, then we see triple alpha giving us carbon 12, and now carbon 12 and oxygen, and then gives neon and so on. So you can see that every time a helium or an alpha particle is kind of interacting, we get a higher and higher element. And finally, we see that if we want to go beyond iron and nickel, we need something called R process and S process, which you have discussed already, and which we can also look at. So yeah, so this is the basic idea, is that big stars are like ogres. So if you remember in Shrek, they say that ogres are like onions, they have a lot of layers, and that's exactly what's shown in this image, is that when you have a big star, and by big you mean massive, which can fuse elements all the way up to iron. In those cases, we find that it will not just be these few shells, there will be multiple shells corresponding to each stage of burning the star has gone through. And we see that we have a core which is fusing, which is usually has gone all the way up to iron, surrounded by shells which are undergoing burning in different stages. And makes sense, because at the core is where we have the highest temperature, and beyond that we have the temperature going down. So in the outer layers, the temperatures may not be hot enough to have the reactions which are happening in the core, but it may have some other reactions which are not really there in the some earlier reactions which don't need as much temperature. So you can also see that as we go to the higher fusion, the rate becomes much rapid. So you can see that the fusion of hydrogen, for example, takes millions of years, and in the case of our sun, as we all know, it takes billions of years, because you know that for another 4 billion years or so, the sun is going to be in the main sequence. Whereas you can see the fusion of helium, from millions it goes to around 100,000. So there's already a order of magnitude difference. And then once helium fuses, we see that carbon fusion takes even quicker. Nitrogen, oxygen, it takes only a matter of years or months. Fusion of silicon, which eventually gives iron, is a few days. And then once we reach the fusion of ion stage, they have written run. And the reason for that is, if your star is so energetic or has collapsed so high to start fusing iron, then you are basically in a supernova stage. You are going to have a huge explosion, and that is why they have mentioned to run. So I hope that now we have a picture, I think this is again and again I'm saying, this is kind of a complementary lecture to the second lecture. The second lecture, we kind of explained all these things sort of qualitatively, that this might, there might be fusion happening in a shell or something like that. Whereas here you can see that we have actually kind of listed out what are the reactions which happen and at what temperatures. So you don't have to memorize the temperatures. I don't think you need to. Just remember some key values, and just remember that, we have these stages essentially. I think that is more important to remember, that hydrogen fuses followed by helium, followed by carbon, then nitrogen, oxygen, and so on. So this is about your stellar nucleosynthesis. But of course, nucleosynthesis is not restricted to stars. So I just wanted to show you an example of a type 2 supernova. So just to recall, type 2 supernova is what happens to massive stars like this layered star when they die. So essentially, when the star dies is when I'm saying there's no more nuclear fusion. So the star entirely collapses, and that collapse can actually bring about, trigger something called core collapse, which can trigger a huge release of energy and a huge explosion, which we call a type 2 supernova. So I'll just play this video. I've also linked it because that kind of captures that. So I just
Massive stars generate energy by the nuclear fusion of elements. When these massive main sequence stars reach a certain point, they will have a sudden and rapid core collapse.
Okay. So core collapse is when the fusion happens, and neutron degeneracy. So neutron degeneracy we have already discussed when we discussed neutron stars. But basically, apart from gravity, to balance gravity other than nuclear fusion, an extra process comes in when we get to very dense states like compact stars. This also I discussed. It's related to fermions and Pauli exclusion principle, and this was discussed, I think, in the second lecture as well. So I just want to show you this so that you can get an idea.
To detach the surrounding stellar material, forming a supernova explosion. This is an example of what a type 2 supernova would look like.
So you can see that huge matter is huge matter is ejected out in a short span of time, and because of that we see this shock wave, and what is left behind is just the neutron star or a black hole. So it can be either a neutron star, it can also be a black hole, and this distinction we discussed also in the stellar evolution.
These neutron stars are extremely hot and are supported against further collapse by quantum degeneracy pressure. Their size is approximately equal to that of Hilton.
Okay, I think the rest of it is there. So I just wanted to show you a visualization of, and I think we already talked about this Crab Nebula and other things, which are actually remnants of the supernova explosion that has taken place. It leaves a sort of afterglow, and those lead to very beautiful pictures, which eventually end up as desktop and phone wallpapers, right? So yeah, I just wanted to show you about type 2 supernova. And during this process also a lot of elements and a lot of new interesting nuclear stuff can happen, and that we will discuss towards the end of today's lecture. So sorry, let's just go to the next slide. So yeah, so before we move to solving problems, I just want to show you this image, which I think I showed you in one of the very early classes. And again, as I said, this is a nuclear astrophysics course. So at the end of this course, one nice goal to have would be to understand where the elements come from, right? And from an astrophysical process perspective. And here you can see that, there are certain elements which come from the Big Bang, some elements which come from dying low mass star and white dwarf supernovae. You can see that dying high mass stars like type 2 supernovae, which we saw. And you can also see some interesting things like merging neutron stars and white dwarf supernovae are also playing a role in the elements. So it is not just that all elements are produced inside stars. We say that we are all made of star stuff, but while that is true, it's not always made in the main sequence of the star. It can be formed well after its death and its collapse, and in fact that is where most of the very interesting rare elements come from, is from higher order processes that happen after the main sequence. So I have another sort of video to kind of visualize that, but that we can look at after solving the problems. So yeah, I just want you to have this image in mind, and I think this is a nice like sort of thing to have as a goal of this course is to understand this image and look at it in more detail. Okay, so now let us do some questions. So as usual, I think today's questions, as far as I saw, and this assignments questions are very mostly like theoretical. So I don't think you will need to do so much solving. So I expect that you guys will answer faster when I show the question. So I will show the question and I want you guys to answer in the chat. Okay, so let's go to the first question. The lifetime for dissociation of beryllium into two alpha particles is? Please write your option in the chat. Okay, I see one person says C. Any other answers in the chat? Okay, one more C in the chat. Others? I think it is a Saturday, so there are a few less people than usual. But in that sense, I think everybody should answer. I'll wait 2 more minutes in case, 1 more minute in case anyone wants to answer. Any other answers, guys? Please put, I want to know if you're listening. Only 2 people have answered. I think at least one more person can answer. And this is something that I discussed it just now while discussing triple alpha also. So okay, I mean, we can move to the answer. Please answer the questions. Otherwise, it's difficult for me to understand if you're listening or not. And yeah, I give you the opportunity to answer because then, if you answer and then get it wrong or get it right, it's easier for you to understand. Okay. So the answer is 10 power minus 16. Okay, someone else said 10 power minus 14. So it's actually 10 power minus 16 seconds. And you can check this in the lectures. And also I had discussed it a little bit before. So yeah, it's a very quick thing that beryllium 8 dissociates. It's an unstable nucleus. And that's why when it captures alpha particle, that forms a sort of, again, an unstable carbon 12 state, which, or a resonance state, which is what is called the Hoyle state. Okay. So again, the approximate resonance energy for the capture of alpha in 8 beryllium to form carbon 12. So what is the resonant energy? This is very much related to Fred Hoyle and what he proposed. Please put your answers in the chat. Okay, I see someone says C. One more person says C. Any other answers in the chat? Others, please answer as well. These are theoretical kind of questions, so everyone should be able to answer immediately. Okay, I see C. I'm gonna wait because I want more people to answer, not just the same people every time. And as I said, this does not require any calculation as such. We have actually discussed this energy right now. So please put your answers in the chat. Okay, please answer, guys. I'm moving to the answer. The answer is 7.6 MeV, and I think I showed this in the previous slide. I can show you. Yeah. So this is about the lifetime of beryllium. You can see it's of the order of 10 power minus 16 seconds. And this is exactly what Hoyle proposed, is that the exact energy of these two might combine to form a 7.65 MeV state, which is what is called the Hoyle state. Okay. So again, I think this is also, I may have just shown you the answer. The approximate resonance energy for the capture of the spin parity. Oh, sorry. I made some mistake. Yeah, I mean this. Okay. Sorry. Yeah, the spin parity of the Hoyle state. Please put your answers in the chat. Those of you who are here, please put your answers in the chat. I see 9 people are there in the meeting. Okay, I see one person says A. Others? Others? Other people? I only see one answer in the chat. It'll be good to see more people, and it's always the same person who's answering also. Okay, one more person says A. I'm looking for at least 3 more answers. These are simple questions, right? We have discussed the questions in some detail. So please, yeah, please answer possible. Any other person in the chat who wants to answer, please do so. It will be good. Okay, maybe because it's a Saturday evening, you guys are tired. But yeah, please answer then, and then only. Yeah, okay. I see one more person has said A. Thank you. Okay, I think 3 people have answered A. That is the correct answer. Again, I made some mistake while writing the question. But yeah, the spin parity is 0 plus, and this was what was predicted by Hoyle, and this was later verified by experiment at Caltech. They actually, you can measure the parity and spin of a state, and they found that it was exactly in the state and in the energy that Hoyle had predicted.
Ma'am,
Okay.
ma'am, I had a question there.
Yeah, tell me.
Ma'am, that question was also there in the 6th week assignment, but when the answers came out, it was 1 plus. I gave it 0 plus only, but they said it is wrong and it is 1 plus. I don't know
Okay,
why.
that
In the
should not
assignment.
that should not be the case, right? Hoyle state has 0 plus. And I think
Yes, ma'am.
in your lecture also it is like that, right?
Yes, ma'am. It was 0 plus, but in the assignment they gave it a wrong and
I think
they said.
I think before also there was some mistake in the assignment, right? Someone had written to me.
Yes, ma'am.
I had told them to check it, and then I don't know if it got resolved or not, because there was some calculation error in the assignment before. So the issue is that I only take these sessions. I don't correct the assignment or prepare the solutions for the assignment. But please write a mail. I will also write a mail about this. So this is which question?
Ma'am, before one, that Hoyle state in carbon 12.
Yeah, that's what. In your, I'll just note it down. Assignment 6, which question is
Ma'am,
this?
first question.
First question. Okay, okay. And yeah, I mean, that is definitely wrong. Other maybe a calculation mistake, but this cannot be the case, right?
Yes, ma'am.
Assignment 6, question 1. Yeah, I'll mail this. I'll also ask about when I ask about the question paper thing, I can mail about this also. But yeah, the issue is that I have to mail someone, and they have to mail the TA who is doing the correction. I don't have the contact of the TA directly. So maybe it will be faster if you guys can itself mail. Maybe you can mail either professor or you can mail any of the NPTEL people to help you out with this. Because yeah, this is not done. This is should be Hoyle state is 0 plus. So that is the thing. So maybe I'm just saying that I last time also one student had approached me because of this kind of discrepancy in like my problem solving session and the assignment. And I actually first checked my session because I can always make a mistake, but I found that their problem solving they had made some mathematical errors. So I had contacted one of the NPTEL staff that I talked to, and they said that they will check it. I don't know about after what happened after that. I did not get any follow up. So yeah, for me it is a little difficult because I am not directly contacting them. So I will suggest that you write a mail, and maybe if all of you are facing this issue, you can all write so that they understand it is not just one student's problem. I will anyway bring this up to them, say that the question was wrong. And you're sure that the question was wrong, right? It was showing 1 plus. Are you sure about that? Does anyone else also face this issue, or only she faced the issue?
Yes, ma'am. For many weeks, these problems were repeating.
Okay.
Um,
So like I can always make mistake, that is there, but as far as I saw, like I try to like check it and all that. So maybe, yeah, maybe it will be better if you as the students can also write. Because as I said, when I have to contact one sir in IIT Madras and he has to contact the relevant person. But you must have some person to contact, right? Who corrects your assignment or something. So you can directly try to contact these people. And they release the solutions, right, of the assignment. So in that, do they give any explanation when they give this wrong answer?
Ma'am, in the solution, the answer is right, but actually, when we submit our assignment, that is marked wrong.
Okay, okay. So basically, you're saying that the answer is correct, but for there is some problem in their marking system. Maybe they have automatically given some option is correct, and maybe in that coding or something, the problem has come. So it might not be the fault of the TA. It might be that A and B might have got interchanged when they were putting or something like that. So yeah, I will say that I can bring this up for sure. I have actually brought it up already because of one of your friends mailed me, but after that I did not get any follow up from NPTEL, and I can understand why, because the people I contact, they manage all the courses, right? So it is difficult for them to search for my course alone and do. So we have a different person who manages. So I think for you guys, if you guys can directly contact, either you can contact the professor, or if there are any TAs who other than me who take the assignment solutions or answer in your discussion, you can contact them. Okay, someone has their hands raised. Please
Hello,
go
ma'am.
ahead.
Yes.
Yes, yes, please go ahead.
So there is a facility for called groups, Google groups, where we can actually raise our concerns. And when we raise the
Huh.
concerns, they told us that there was some the answers are correct, but at the same time there was issue with the correcting procedures. So at the end of the day, while they'll correct all these and they'll upload the real marks, that's what they told. So
Okay, okay. So this
need not
has,
worry.
yeah.
That's what they said.
So that is what I also guessed, because someone said, right, the solution sheet has the answer correct. So it must be something there must be an automatic marking, and that marking the option must be wrong. So I'm sure that if you have got that kind of assurance, I'm sure the NPTEL team will follow up and do it. So I will also just remind them that students have been saying this, and if that message gets communicated. But yeah, you please use the discussion forum, and you yourself like directly also bring this thing up. Because I think the assignment will eventually have some role in your exam and all that. So please make sure that everything is fine before your exam. And yeah, so don't get confused because of seeing a wrong answer that what you studied is wrong. You should have the confidence that what you studied is correct, right? So yeah, always just verify if it's correct, and if it is correct, then it is your right to question the solution. Anyway, so that I will definitely, I've noted down the question and I will mail them about it today itself after the class. Okay. So the next question is, which of the nuclei did not form during Big Bang nucleosynthesis? And this actually again was answered in that periodic table that I showed you. So there are a couple of answers. It's not just one answer here. So please give all the answers that are relevant here. Please put your answers in the chat. Are there any answers? I don't see. Okay, wait. Okay, I see C and D given by some. Yeah, okay. So I see, okay. Many of you have answered C and D. For some reason, it didn't load for me. Now it has loaded. So yeah, all of you are correct. It is C and D. So during Big Bang, if we go back to our periodic table, you can see that, oh, sorry. Can see that the Big Bang actually only produced these two elements, hydrogen and helium, and that is called primordial nucleosynthesis. And then beyond that, what we saw is that whatever has happened in the interiors of stars, either small stars or heavier stars, or through the merger of stars or something like that. So we started off with hydrogen and helium, and through fusion reactions only we got the higher and higher elements. Okay. This is the next question. Again, this is an easy question. Please answer in the chat. I see people saying C. I'll just
Hello.
wait in case more people are answering.
Hello, ma'am.
Please tell.
Regarding an earlier question, there was a question that there was asking about the approximate resonance energy for the alpha capsule and 8 beryllium, right?
Which one? This resonant energy. Yeah.
Approximate resonance energy.
This one.
Yes, ma'am. So I think this one is also a multi-correct correct answer, but I know
Okay.
that this NPTEL people can get it wrong, but with that being said, only 7.6 is the right answer, right, sir? Right, ma'am?
I think 7.6 is the right answer. No, the Hoyle state is a state with energy 7.6. So in that sense, I think that is what the question is leading to. I may be wrong.
Ma'am, regarding the when you look at that scheme that you're talking about, isn't there a second excited with 4 point something maybe?
But the point is that that comes because of the decay of the 7.6, right? So I don't know if that can be called. So beryllium and carbon are resonant with the 7.6. Like the 7.6 is the energy that is formed by their thing. I don't know if 4.6 is also an answer. I should look it up. I can check it and maybe update the slides, or I can check it right now also. But as far as I saw, it was 7.6 only. So was there a multiple answer in your assignment or something?
Yes, ma'am. This was asked as a multiple answer. So I had a doubt if 4.6 will that too come in the answer? And after the correction, the NPTEL guys have given that 7.6 and 8.6 is the. I don't think that is right anyway.
Okay. Okay, I don't know. I also take these questions from last year's assignment. So in that, this was the only answer as far as I remember. I can just check it one sec very quickly. Let me just see if I have it open. No, one sec. Yeah, in all the energy diagrams that I see, I only see 7.6. I see a 4-point kind of state, but that comes from the decay of 7 point. I don't think that can be an answer, right? Because we are talking about the resonance. The resonance is with the 7.6 stage. And okay, one sec. Let me just share my screen again. Yeah, so my point is that most of when I was preparing this lecture also, all the diagrams I saw were like this, where there is a 7 point something state, there's a 4 point state. But I don't think it is right to call this 4 point state as a resonance condition, because the resonance is between these two states, right? Like this energy and this energy are resonant with each other. And that is what was remarkable about Hoyle's thing. And this decays to 4.4. I don't think that's right to call it resonance. So I don't think 4.6 could be an answer. About 8.6, I can't find. I did not see anything where 8.6 itself was involved. I have to check. So in your solutions, they have given 8.6 also, is it? So was
It's
there
not like
any?
solutions. They have just corrected. They have just corrected. Given half
Okay,
marks
okay,
for
in your
7.6.
okay, I understood. So in your lectures, was this mentioned at all? Because I also follow the lectures sometimes. I don't remember seeing 8 state there.
In the lectures also, this is the exact diagram that we are given. The
Yeah,
7.6.
so that's what. If I just now searched online to see if anything is there, I just did a very fast search. So maybe I missed something. But as far as I saw, this is the standard diagram, and this is the one where people use. I think Hoyle state, the point of Hoyle state is that there is a resonance, right? It should not be multiple states. I don't think that makes sense. Also, yeah, let's. What question number is this? I will mention this also when I mail them. Again, I don't know if they will respond to me, but question number of this question is, so already one of your friends said question 1, assignment 6. And the one on resonance, right? Okay. I will check the question number and I will let them know that there might be something issue. And please, you also independently bring it up on your Google discussion forum or whatever it is, so that maybe there is something that we are all missing, right? There could be, because this is somewhat new to me also. So maybe there is some extra state. As far as I know, there shouldn't be, because the philosophy behind resonance state is that there is one state which is kind of acting as an intermediary. But yeah, we have to, maybe there is something else. So just, yeah, please bring it up to them. I will also try to bring up that some questions seem to have contradicting answers. So I think we were in this question. I think most of you said C, which is the correct answer. So again, triple alpha does not happen with 3 alpha particles going together, but we actually see 2 alpha particles which first form beryllium, and that beryllium captures an alpha to form further carbon. Okay. So this is the next question. Please answer it in the chat. And yeah, don't worry about at the moment the question answer thing. you guys follow your lectures, look at books or other resources on the internet and try to make sure everything is consistent. And if you find any inconsistency, please you guys bring it up. It will be good if all the students together bring it up. They can understand that there's an issue. I think they have already said that there is some issue, so they know that there is some issue. It could be that this is also part of that also. So yeah, I don't think it's right to call 4 as a resonance state. In my very naive view, I'm not in this field exactly, but yeah, I can check it. If there is anything extra, I will update the slides also when I upload. Okay, so I see that people are answering B. Okay. Okay, yeah, I think 3 of you have answered. The answer is actually C, in the sense that, where is that slide? Huh. So the lifetime of beryllium is longer than the scattering of the helium nuclei. So here, what was the question? Yeah, so the lifetime of alpha particles. So in that sense, they are saying the scattering process happens fairly, where was it? Where is it? Let me just give you that. So basically, the lifetime of beryllium is longer than the collision or scattering of the helium nuclei. That is why they are able to capture, right? Otherwise, they will not be able to capture. So that is the point. But here, I don't know if that is exactly what they mean. Let me just look at the question again. Answer of two particles. So that's why it is C, because of this thing. Because it has to be longer, otherwise it will not capture another alpha particle to take place in the next reaction. Okay. So the next question is this. This is this is kind of like one of the questions that we have done. Oh, sorry, I showed the answer. Okay. Regardless, please solve the question. I think this should be 10 to the power. So this is like one of the questions we have been solving in the past few weeks. So you should be able to do this. I'll give you a few minutes to solve this question. Please proceed. Okay, one person says B. I see one more person saying B. Anyone else? Any other answers in the chat?
Hello, ma'am.
Yes.
Regarding the previous question, in the lecture, Sir actually talks about this temperature range, and then he talks about the transit times between alpha particles being about the order of 10 raised to minus 19 seconds, and
Okay.
the lifetime being 10 raised to minus 16. So,
Okay. So transit time is 10 power minus 19, you're saying?
yeah,
Okay.
yeah.
Then maybe I misunderstood the question. I thought it is related to that alpha particle bombardment. Maybe this transit time might be something different. So yeah, if it is in your lecture, then probably that is correct. I am kind of, as I said, I am also kind of new. I will check that and I will let you know also about that. So,
Okay, ma'am.
okay. So yeah, I was thinking about more of the thing that the beryllium has to exist for the alpha to impinge. So that's why it should be longer. But I guess this is two alpha particle. Maybe that's why I have to think about it. Let me look at this and I'll update it after the class. So any other answers about this question? I think we can go to the answer. The answer is B. Why I didn't Yeah, so the way to solve this, I think by now you should all be experts of solving these kinds of question, is that the number density kind of is given by the or the number of particles you can find in this way. It's the mass fraction. This is the Avogadro number, and rho and A are the densities and the atomic numbers. So basically, you are finding what is a fraction. You have the you have the mass fractions, but you want to find the actual number of particles. So that's why you have to put in back all these terms to get back that idea. And then if you find out that all these rho and Na will cancel out because they're basically constants, and you find that it depends basically on the mass fraction and the atomic mass number of the system. And if you find it, you find that the answer comes to be 10 power minus 10. So this kind of question we have done a lot. Again, this is more of a number counting kinds of problems rather than any nuclear physics or astrophysics. So please be careful when you do these questions and try to remember how to do these questions. Okay, so this is the question. Next question. I think this is the same question again. Maybe. So please answer. Meantime, I will check about that transit time thing. Yeah, sorry. I was just looking at that question. I'll just clarify it also. Okay, so yeah, many of you say A, which is the Hoyle state, as we had discussed in some detail. So the Hoyle state is what is responsible for the resonance condition, which allows the beryllium process to complete the triple alpha fusion that we see that leads to formation of carbon 12. Next question. What is an example of an alpha conjugate nucleus? So these are, kinds of clustering of alpha particles. So you know what an alpha particle is. This you can do by, again, this is kind of a counting process. So any answers in the chat? Anyone? So alpha conjugate nucleus, I'm just replying, repeating, means that they are groups of alpha particles, or they're clusters of alpha particles, and they can be decomposed like that. So if you look at these particles, which of these, or these these nuclei, which of them seems to be alpha conjugate? Okay, I see one person say E. Others? Okay, one more E. Okay, fine. I think you guys are answering. The answer is E. Yeah, the answer is E because this can be thought of as 4 alpha particles essentially, as the others can't be broken up into alpha particles in that form. So it's 16, and you know an alpha particle has a mass of 4. So that way you can think about how it can be divisible. So this is the last question. Yes, so this is something I think we discussed in maybe the very first class also. And we said that this is kind of an evidence that nucleosynthesis is happening in stars. And particularly neutron capture is interesting because we saw about, for example, this island of stability last time. And you know that when we go to higher and higher elements, there are more neutrons than there are protons. And so when we add neutrons, we are able to reach, at higher elements, we need to add more neutrons, and that's how neutron capture happens. So the answer is tectinium or TC, and that is the answer. And that was kind of because as I think we discussed in the very first class, this is an unstable isotope and so on.
Ma'am, this
Yes.
question was also asked in the 6th assignment, and I have given the answer of tectonium, but they marked it wrong and gave it to be aluminium.
Okay. So as far as I know, the answer should be tectinium. So why don't you ask them to release the solution set and then you can recheck, so that because as far as I know, tectinium is what proves, right, that there's active nucleosynthesis happening in the star. So you can ask them again, just add it. I think now there are 3 questions that we have to, that there are some discrepancy. One is your Hoyle state question, the other one is your resonance question, and now this question. So please make a note of what is the question number and ask them to release the solution set. I think that will be the best option. And if you find that, like before, the solution has the correct answer, but the marking has the wrong answer, then you can very easily tell them that please do the marking again. But if the solution has the wrong answer, again, I am also following some notes that was given to me by the NPTEL team. In this is the solutions that I have got, and I have also checked them myself, and I feel like they make sense. That's why I have included them. So please, you also just check your answers, and you can check with the team directly. Again, I'm sorry that I am not able to help directly. I am not in charge of this, so I cannot do anything. I can also just ask the team. But as I said, for me, I have to ask someone to ask someone else. So it will take time. Whereas if you guys ask, I think you can directly ask whoever is in charge, and that will be more efficient. So please try to do that, and I will definitely bring it up after this meeting. I am definitely drafting up a mail to address all these points, but I would say that you guys also use your discussion forums, and please give the feedback to them. Okay, and again, you should not change your answer based on something else unless you are convinced. So did you get convinced that aluminium was the right answer, or did you think it is right because someone told you? So you should make sure that if you're wrong, you should know why you are wrong also, right? So in situations like this, we may be right. It may be that the system has made some mistake. Doesn't mean we should think we are wrong. Okay, so that is about this. I will definitely check this. Okay, so that is the questions of today. I'm just showing this again because I wanted to discuss some extra things today relating to formation of heavy elements in stars, and I found very nice video to discuss. But before going to all that, just to address the things that, because there have been a few people who have been saying this, I'll just summarize. Basically, we have seen for some assignments that there is an inconsistency not only in the marking but also within the marking and the solution scheme itself. So that means that there is some issue with the marking that is happening. It may be automatically marking, and maybe the options are given slightly wrong or something when coding it, right? So I will say that I can bring it up to the NPTEL team, but as I said, I have only one point of contact, and that person handles all the courses. So that person has to then contact the TA. I do not have a direct link to the TA. So that is a little bit difficult for me. I would suggest that you guys please write to instructor and write to the Google discussion or wherever you get your answers from, and bring these points up. And if one person writes, please others also kind of write in the comments or something, so that people, you understand that this is a problem that all of you are facing. So again, I will write, but for me to get the answer, it will take one person contacting another person, whereas you can contact directly. So this is about the assignments. Don't worry, we'll find a solution. We can write to the professor also. But as far as I understand, this is not a fault of anyone. This is not a fault of professor or the TAs who are setting the assignments. This is some computer error where the computer is marking some wrong questions because of some coding error or something like that. So that can be easily rectified. So just make sure that they are aware that this is a problem that's happening. So if you write also, please all of you like write, so people understand that this is not a problem of one person, but everyone is facing the same problem. Okay.
Hello,
So
ma'am.
this is about, yes.
I checked just now, and one student has already completed that. A lot of questions that were submitted in week 6 assignment does not match with the source material, and they have actually replied that the accepted answers will be reviewed and the final evaluation will be done for correct and only. Please submit your assignments without any worries in the future also. So they have actually clarified it.
Okay, so they have clarified it. Okay, that's good. So thank you, Vivek, for telling us that. So as Vivek said that they have already clarified that. So you please like wait for the solution sets, because solution sets are prepared by TAs, right? They are not prepared by machine or anything. Machine can make a mistake while marking your answers, but the solution set will have the correct answer. So please wait for the solution set and see if the answers are matching. Even then, if the answers are not matching, it may be that you or I have made a mistake, right? So again, I am also not kind of new to these things. My field of research is a little different, so I am also learning with you. So in that sense, I can also make mistakes. So please feel free to like write to me if I have also made any mistake. I will say that much. Okay, so right, so we have done questions and we have seen about the reaction. So now I just wanted to show you something extra, because I came across this video when I was preparing for today's class. And it's basically about these higher elements, right? Not about this star which are produced in the stars, not up to ion, but beyond that. How are those elements exactly coming in, and how do their abundance come in? So it is not very straightforward. We just think that it is produced in supernova, but it is a little more complicated than that. The reason that I thought I can show you this video is because yeah, so this is a video that from this channel, But Why, and they have nice explanations. And I have also linked another video which is about supernova type 2, not directly related, but it is relevant. And the first part explains supernova process very well. And I think that that could be helpful for you if you want a sort of visualization, if you are kind of that kind of person. And the point is that this video, it when you watch this video, it will have a lot of the concepts that we have been discussing from the very first class are all brought together in this sort of video. So let me just play it. Maybe I can just. At the beginning of the universe, all atoms all atoms in existence possessed only one, two, and very rarely
3 protons.
So this is about
Over eons, gravity brought these atoms
primordial
together. Via
nucleosynthesis.
extreme pressure and heat, they fused in the cores of first stars, creating larger elements.
Right.
But this fusion can only squeeze about 26 protons.
So I want you guys to like check how many of the concepts you recognize, right? So right now we're talking about fusion up to ion, which is something that we have talked about. And this is about how the other elements. So this video is about how the other elements really come in. So
Iodine and selenium, although trace elements in the human body, are critical for our existence.
I'll just skip
Entire
this.
technologies are based around the availability of rare earths, like prized above others. But where do these elements come from? Why are they so rare? The most prevalent pop science explanation for their origins are supernovae. Although this is not incorrect.
So these are like simulations of people doing supernova things. And there's another video on this, which is nice.
Stars can only get hot and dense enough to form iron.
Yes.
Simply need
So this we have already seen that iron is the maximum that you can form in a
this
stellar
is solved thanks to the extreme heat and pressure of supernovae.
Right.
But elements heavier than iron, especially the more massive ones, aren't formed from fusion. In fact, temperatures hotter than those needed to fuse iron produce photons with enough energy to fragment and split these atoms into smaller ones. So hotter and denser environments are actually counterproductive to the creation of heavier elements. Instead, these elements are formed from a much more interesting mechanism called neutron capture.
So I think you guys would have heard about this neutron capture in your lecture. That's why I brought up this this video for you
Nuclei
guys.
are held together by the strong nuclear force.
So again, these are concepts that we have all seen already. Strong nuclear forces coming in, for example.
But protons repel each other and neutrons are less stable.
And we know the reason for this. This is of
means
course the
most
Coulomb
stable nucleus
repulsion, and we have
is
seen this
a
already.
combination of protons and neutrons. Let's look at an example. If
Okay,
we
so
were
I
to
think we
merge
can
two
skip this.
protons attract each other, propulsion, state into a neutron remains. In the case of people, a tritium is adding either a neutron or proton contribute ratios of the most common.
Yeah, so this is basically the island of stability that I spoke about last time, right? So you can see that the lower mass isotopes or lower mass atoms have neutrons and protons equal. But as you move higher, like the neutrons dominate much more than the protons. And they give a nice explanation of why.
That holds
So
nucleons
that's why I wanted to.
together only acts over a very short distance. Whereas the Coulomb repulsion felt by the protons extends over the entire. That means a proton is strongly attracted to all of its immediate neighbors, but repulsed by every.
So yeah, so it has to do with the fact that they are short range and long range forces, right? The strong nuclear force, even though it is much stronger, it is still a short range force. So it only acts on the immediate neighbors, whereas the long range force is a Coulomb force. So essentially what they're saying is, if we have a lot of protons in a system, which is what happens for high atomic number, right? Then the Coulomb repulsion, even though it is less strong than the strong nuclear force, is still significant because the Coulomb repulsion happens between all the protons, whereas a strong force only acts between the pairs which are close to each other. So to ensure that the Coulomb force does not, throw everything out of balance, we need enough neutrons to compensate for that through the strong nuclear force. So because neutrons are neutral, they don't have the Coulomb force happening, and that compensates for this high number of repulsion that comes because of the high number of protons. So this is a kind of idea for why, n greater than z happens in the higher mass cases. So I thought this is a nice explanation and I wanted to show you guys.
Repulsion, every other proton.
So yeah, I think they just explained this. I can go forward.
Large
Yeah, so this is the explanation. You guys can go and watch this. It's a nice video. And then I'll just skip to where they.
neutrons to large elements is the back.
Yeah, so this is.
Firstly, the harder it gets to add more protons.
So the idea is
This
that we get
ability
to add
easily add
more
extra
neutrons, and that
neutrons
leads to
large
neutron
elements is
capture.
the backbone of neutron capture and the mechanism for creating larger elements. Neutron capture can occur either slowly or rapidly. The difference.
And I think you saw this S and R process already in your lecture, the slow process and the rapid process. The slow process is where a neutron is added and there is enough time for it to stabilize, whereas in a rapid process, we see a lot of neutrons are added at the same time and then we see a decay which could happen.
For slow capture, neutrons are added slower than the decay lifetimes of the new isotopes. Capture events occur on intervals of 10 to 100 years. So,
I think you would have covered this in your
if the
lecture,
current
but it's a good
isotope is
recap to
there
have.
is typically a decay before the next capture event.
Yeah, so there in
This
a slow
increases
process,
the
we
number
have
of
decays and
protons
captures happening kind of back to back.
This
Whereas
slow addition of
in a rapid
neutrons
process,
occurs
there's a
when
lot
the
of
outer elements
neutrons
find
adding.
themselves in an environment with free neutrons floating around, like the fusing regions of giant stars. Because neutrons are added so slowly, S-process elements always have a ratio of protons to neutrons that hovers around the line of stability.
Yeah, because S process is like very slow. It just always forms an equilibrium or a steady state. It does not form anything that deviates too much from the line of stability.
Stars, which then exploded, usually from type 1 supernovae, are the seeds for much larger elements.
So this is a very interesting point because this is something that was covered all the way back in the first lecture. If you recall, there was this discussion of population 1, population 2, population 3 stars, and we discussed how population 2 stars, maybe population 3 is still like hypothesized. It's not really observed, but we know that there are at least 2 populations of stars, right? One which formed very early in the universe, which are less metallic, and then the population 1 stars are formed more recently, and because of that they have higher metal content, because the stars which have died before them and exploded in supernovae, they have enriched the matter with metallic, that means higher order elements, so the stars form with more metal content and they are younger.
The iron can
So
condense along
this is what
gas
they are
to
also
form a
saying.
new star.
So that's what I meant, like everything you're learning is kind of connected in the end. So you have everything connecting together. The S process happens because we need we need an environment with a lot of neutrons, which is facilitated by the sort of population stars that we were talking about earlier.
As the star carries on with its life, these large elements are then ejected back into the cosmos via stellar winds.
So this is kind of like the feedback mechanism from where the winds are enriched by the previous stars dying.
These heavy element enriched.
And that's what this is important to study populations, different populations of stars differently.
The second mechanism for neutron capture is the rapid process. This is when atoms are bombarded with neutrons, accumulating dozens and dozens of neutrons, producing bizarre and highly unstable nuclei. These nuclei will then decay on a longer time scale back towards the line of stability. Each neutron that decays produces a new proton and thus a heavier element. In order to bombard nuclei with so many neutrons,
you need a very neutron-rich process
environment.
Incredibly
high neutron
so where do those happen?
The two most likely candidates for these locations are the neutron-rich cores of supernovae and the neutron-pure environments of.
So basically, inside a neutron star or in a supernova is where you see this high amount of neutrons happening.
During these events make neutron accumulation in almost.
And that's where our process happens very efficiently in these sites.
Atoms will be able to escape.
And particularly in neutron star mergers.
Aftermath and the frequency of their occurrence throughout the history of the universe.
I think we can.
However, we expect the rate of neutron star mergers will follow the history of star formation in galaxies, with a few 100 million or so year delay for those stars to die in our galaxy.
Yeah, okay. So let's.
Greater frequency than neutron star mergers. Models suggest the latter is actually the source for the majority.
So that's nice thing is that, you know, I think I saw a quote or some like gravitational wave physicist saying that, you know, the platinum or the gold ring that I'm wearing on my finger came from a neutron star merger. So, you know, even though we think of supernovae as being the sites for where a lot of them come from, but if you look at the previous slide, okay, so if you look at the previous slide, you can see that even a lot of them also come from the merging of neutron stars. So dying high mass star is kind of your type 2 supernova, and you're merging neutron star. And you can see that, you know, some of the very higher elements like platinum and so on, which is what that physicist talked about. See, platinum in the ring comes from merging neutron stars. I think that's what they said. So that's a nice thing to talk about. Yeah, so I think we can just. Oh, it's not playing. I don't know why. Okay, I think some issue in the video is not playing now. But yeah, I think you get the point. The point is that there is this different processes that happen for formation of higher order elements beyond iron, because we know they can't just form from stellar nucleosynthesis. And two of the processes that are involved are S process and R process nucleosynthesis. And we saw the sites where these are kind of likely to happen. So we also see that the population of the stars and their dependence on their metallicity, their enhanced metallicity, all that comes into the picture when we talk about how the elements are actually formed. And I would suggest all of you to watch this video. You can also watch the other video, because I thought that it was very nicely animated and explained. And yeah, sometimes visualizing things helps us to understand things better, at least for me. So yeah, I'll just go
At
to
the
the
beginning
oh.
of the universe,
Now it's
all
playing. Okay, fine. Leave it. So yeah, I put all the links in all the slides. Please go and watch them. I always put a lot of links in the slides. I don't know if you guys are using them or not, but I sometimes put links that may not be useful, may be useful, but are always interesting to me at least. So they may be interesting to someone else. So you can see here, these are the sort of proposed population 3 stars which have not yet been discovered, if I'm not wrong. Any stellar, I don't know about the current status of stellar physics with respect to the detection, but as far as I know, I remember these are not detected, they're still hypothesized. Of course, when these stars died, they released a lot of new elements which form the population 2 stars. When these further decayed, you know that supernovae can undergo our process, and also the um, merging neutron stars. And you know that in low mass stars like type 1 supernova and AGP phases can lead to S process, which is a slow capture of neutrons. All this can lead to further and further higher elements. So you can see that the metallicity of stars grows with time, and this is exactly what is there. And I took this from this link, and the explanation is given here. So yeah, so this is just, I wanted to include this because of this very famous quote that comes from Carl Sagan, who's pictured here, and he was a very famous science communicator. He had a very famous show called Cosmos, and which is also a book. And he has this very nice other thing called essay of called the Pale Blue Dot, which I encourage all of you to read. But for now, we will end on the quote by Carl Sagan, which says, "The nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in the interiors of collapsing stars, and we are made of star stuff." So, of course, it ends up that we are not all just made of star stuff, we are made of dying star stuff and merging star stuff, and stars doing all these weird things kind of. So that is a very interesting way of looking at things, and I think that we can end the lecture here on that nice note. So just for some housekeeping, I hope that you guys followed today's lecture. As always, I will be uploading the slides, and I will record the video and also upload it on YouTube. Please email me in case of any issues. I will definitely, I think Vivek has already said that the NPTEL team is actively looking at your issue with the assignments, but I will also drop a mail so that they are aware that this issue has been brought up to me also. Apart from that, again, sorry that we had to keep a session on Saturday. This past Monday, I was like away. I was at a conference. I could not take the session. That's why I had to change it. And as I said, because of Shivratri and other things, I think I was not, there were no slots available throughout the week. So the next session will be day after tomorrow on Monday as planned, and it will be about week 7. So in between, if you want me to tomorrow, please mail me if you want me to cover something specific in the week 7 lecture. Otherwise, we will discuss whatever has been discussed in the class and do some assignment problems as usual. Okay, so I think we can end the session Saturday night. So I don't want to keep you guys also very long. So yeah, thanks everyone. I think that's it. So
Thank
yeah,
you, ma'am.
yeah. Thanks. Thanks. Bye everyone. Bye.